Okay, we're in Trig section 8-9, binomial probabilities. And flipping back in my book here for a second. A binomial situation, what is that? A binomial situation is something that has only two outcomes, success or failure. So you'll notice I actually noted the first one, or the second item here. It has two outcomes, success or failure. So that's really the basis of a binomial experiment. You flip a coin, you get heads or tails. You shoot a free throw, you make it or you miss it. You have a cancer treatment, you're either in remission or you are not. So it's more than just, it's not a situation like rolling a die and getting a 1, 2, 3, 4, 5, or 6. It has to be defined as rolling a 2 or not. So you have to be specific, or I rolled a 3, 4, 5, or I didn't, right? So you can define the group of what you call success, and then failure is everything else. But there are really only two outcomes. You're either in the group we call success, or you're in the group we call failure. So a binomial experiment requires that you have what we call repeated situations or trials. Obviously, as I've said before, there are only two outcomes, success and failure. The trials are independent of each other, meaning one trial does not affect another. And each trial has the same probability of success. We use the letter lowercase p to represent the probability of success, and lowercase q to represent the probability of failure, and obviously p plus q has to equal 1 or 100%. Now, if you go back with me a little ways to what we did with expanding in Pascal's triangle, you might recall that when we expanded p plus q to the fourth, we know that p plus q represents 1, so this is like 1 to the fourth. We can look at how it breaks down. For instance, we can write out the fourth row of Pascal's triangle, which we know that these are combinations, right? 4 choose 0, and 4 choose 1, and 4 choose 2, and 4 choose 3, and 4 choose 4. And then we would start with the highest power of p and count our way down until we get to p to the 0, drop down until we got q to the fourth, and count our way back until we got q to the 0, and then multiply everything down the column. And so we could write our probability or expansion out like this. There's only one way to get 4 successful trials. There are 4 ways to get 3 successes and 1 failure. There are 6 ways to get 2 successes and 2 failures. 4 to get 1 success and 3 failures, and lastly, only one way to get 4 failures. So we kind of use that idea in example 1. Example 1, if you look at the book, talks about cancer treatments. The probability of successfully remaining in remission for at least 1 year is 70%. So p equals 0.7. Obviously, that means q equals 0.3. So x, I'm defining x to be, in part A, the number of people remaining in remission out of 4 people. So we have 4 trials, and x represents the number of those people that are in remission for at least 1 year. So that could be as few as 0, and it could be as many as 4. I'm looking for the probability of exactly 2. So if you go back to our chart and you look at what we had here before, we're dealing with this. 2 successes, 2 failures. So we know that this is 6 times 0.7, that's p to the second power. times q to the second power. And if we use our calculator for this, we got 6 times 0.7 squared times 0.3 squared. 0.2646. Well, what if we wanted the probability that x is 2 or 3? Well, we know the probability that x is 2. We got the 0.2646. But now we need to add the probability that x is 3. So that would be 4c3 times 0.7 to the third times 0.3 to the first. So we need to figure out that second part. 4c3 would be 4. We just you can look back at your chart from the other one to see that. So I'll delete that and just put 4. Oops, not even on screen. Times 0.7 to the third times 0.3 to the first. I'm going to So that total probability is 0.6762. 0.6762. Now, the more generic looking version of the binomial probability theorem looks like this. The probability of exactly k successes is equal to the number of trials, combination choose k successes, the probability of success to the k power, and the probability of failure to the remaining, to the number of failures. So these represent the number of successes, this represents the number of failures. And multiply those things together to get your probability. In example 2, we're talking about 8 multiple choice questions with 4 choices. We are purely guessing. So in other words, this is that whole situation where you happen to be taking a graduate level engineering exam written in Chinese, for which you would have no idea what's on the test, so you would be just guessing. So let's see here. We want the probability that x is greater than or equal to 5. So we are going to actually have to figure out that the probability of x being 5 and 6 and 7 and 8. And we have to add those 4 numbers together. Boy, it would be sure nice if we could do this all at the same time. Well, we can. Let's use our graphing calculator to generate some of these things. Get into your lists and make sure you get them all cleared out. We want 0 all the way down to 6, 7, and 8. So in list 1, you want to have 0 through 8. In list 2, we're going to use that binomial probability theorem. All right? So we want 8 trials, and we are using our combinations formula, right? But instead of using a number here, we're going to put L1 in parentheses. Now that's not going to get me what I want totally, so I need to continue, use another parenthesis. We've got, what's my probability of success if I'm guessing and there's 4 choices? Wouldn't that be 1/4 or 0.25? We want to raise that to the list 1 power. Times the probability of failure, which is 0.75, to the, and my exponent for this one's going to look a little interesting because it has to be 8 minus list 1. 8 minus list 1. Now it's going to find all those probabilities for me. Now, if I want to add 5, 6, 7, and 8, here's what I'm going to do. I'm going to come down here. Yeah, won't let me do it. You know, just for fun, at the very end of this, I'm going to just type this, 0.02307. All I'm going to do is I'm going to add these 4 together, if I can, plus 0.00385 plus 3.7. The E that you want to use is above the comma, -4, plus 1.5. It looks like a double E. It looks like a double capital E if you're looking for that button. -5. Well, there it is, 0.02731. 0.02731. So we found a whole list of these numbers. And then at the very end of the list, I went in and I just typed. Now, let's suppose I wanted to add like 0, 1, and 2, I could have just come up here to list 3, and just so I had them on screen, just add the 3 numbers together. It'll put them in that list. Not that you need them in a list, but I just want the 3 numbers so I can add them up. Okay. Now, next thing. Example 3. Suppose P is 0.7. Determine the probability distribution for 5 trials. Well, that's exactly what we just did. Okay? So I pretty much just taught you how to do that, but we're going to only use 5 trials. So I can actually delete 6, 7, and 8 from my original list and just use 0 through 5. And then, as I did before, I'm going to use that binomial probability. Here, I'll get it up in the middle of the screen. Go all the way to the top. 5 Math, NCR, List 1. Probability of success, 0.7. Oops. To the List 1 power. Times the probability of 0.3 to the parenthesis. 5 minus List 1. And those are my values. Okay, so those are my numbers. That's considered a probability distribution. That's it. Nothing more complicated than that. You're just making a table. That's what a probability distribution is. We did that stuff before. We even found expected values. Oh yeah, sum list 1, list 2. That's coming in the next section. Section 10.2. Or I should say 2 sections. But this leads us right into the binomial probability distributions. In section 10.1, all they're doing is taking what you figured out and graphing it. Well, we already know how to do that. We know how to make list 1 and list 2. We just need to take this information we have here and make it into a graph, a histogram. Well, that's not too hard to do, right? What's the highest y value here in our list? Keep in mind it looks like 0.36. Alright? Our window should go from 0 to 5 and from 0 to 0.4. So let's change our window. I actually made it go from -1 to 6 just so I made it a little bit wider in the x direction. But I think 0.4 is plenty on the y direction. You don't need to really go a lot higher. You'll notice that my y-scale is 0.1. My y-scale down here is 0.1. I went up by marks of tenths. All right, so let's go into our stat plot. Make sure that you have a plot turned on. Make sure that it is a bar graph or histogram. And make sure you have list 1 for your x's and list 2 for your frequency. Now when you go to graph it, you're going to see a nice looking histogram. Now I know you're saying to yourself, well, if it's got 5 trials, shouldn't there be 6 bars? Because don't you have 0, 1, 2, 3, 4, and 5? Well, I see 5 bars. 1, 2, 3, 4, 5. The last one down here is so small, it didn't even register on the calculator screen. The pixels, we don't have enough detail in our graph to register that one. There are 6 bars there, though. But here's a picture of your histogram for that particular section. Now, a couple things they want to show you in the histogram, so let me look at the book. The book actually has some nice looking pictures for us. So I'm going to switch it over to the good old color screen. I know, several of you are blinded at this point, but you'll get over it. Now, you'll notice in this picture, whoa, going the wrong direction. You will notice in this picture that all the bars look like they're stacked up on the left side. You'll also notice that the probability of success is very small, 5%. This is considered a graph that looks skewed right. I know that doesn't make any sense to you. You're saying, what do you mean? They're all stacked up on the left. The tail, which would be this, the tail points in the direction of the skewness. So now you've learned a new word, skewness. You can use it at parties. As you increase the probability of success to a quarter, look at what happens to the graph. The bars are getting lower. It's getting more centrally located. Even when you increase it to a 0.3 for a probability of success. Or 0.33, I should say. It's looking more like a smooth bell-shaped curve. Well then we move on, right? To 0.67% success rate. It looks kind of like the one before, but just kind of, reversed in the other direction. And 75% looks an awful lot like 25%, just kind of flipped around. And lastly, we get to the 95% success rate. And it has a tail pointing to the left, so it is called skewed left. Skewed left. So that gives you an idea of how the probability of success will change the picture. What about the number of trials? How does the number of trials change things? Well, all the graphs I'm going to show you here have probability of success 50%. We've just changed the number of trials. So if you have 2 trials, you only have 3 options, right? 0 successes, 1 or 2. This is what it looks like. If you change it to 6 trials, now you should start seeing that it is looking more symmetric, more like a bell-shaped curve. Now if you go up to 10 trials, it's looking a little bit more like a bell-shaped curve. Go up to 50 trials. It looks a lot like a bell-shaped curve. The more trials you have, the closer and closer and closer it gets to what's called a normal curve. Now we will talk about that normal curve later, but keep this in mind. The binomial probability is looking a lot like a bell-shaped normal curve. Okay, and that's all for sections 8, 9, and 10.1.